Hello, this is Jack Jackson. We're back again, and this is the second video in this playlist for uh, Calculus 3, and we're going to be talking about new types of functions. And there's actually several places that we can start here, but I thought the best place to start here is to talk about vectors. In fact, this video could be part of a geometry class or a pre-calculus or trigonometry class as well, because we're only going to be doing pre-calculus stuff here, talking about vectors. So I might use this same video in one of those contexts as well. Okay, so part of the reason why we're going to do this is because vectors are needed for physics quite early on, so it's kind of useful to get some of this information out of the way first. All right, so a vector is a directed line segment. It has both a magnitude and a direction to it. So if we're looking at a 2D vector, it would be like this blue thing here or this red one here. And it's basically just a line segment going from point A to point B. It has a direction to it. So this little arrow here at the end indicates a direction. Now, unfortunately, that's kind of the same notation we might use for a ray, indicating that it's half of a line, that it goes on forever and ever and ever. That's not what we're doing here. The arrow only indicates that we're starting at point A to point B. So there's something dynamic about it, something kind of moving if you want to think of it that way. And here's a different vector here going from D to E would be this vector W. And vector U is this vector blue one going from A to B. So these vectors can be done in two forms. There's a polar form where we give its magnitude and direction. Now vectors oftentimes have several words for the same thing. Magnitude, norm, length are all basically different words for the same thing. The direction is given by the angle that it makes between the vector and the positive part of the x-axis. Now the norm of v, well, let's back up. Just v itself will be given as v with a little arrow over the top. Some other people use a bold-faced italics for vectors. That's fine, but the problem with that is when you write them by hand, it's really hard to tell the difference between just a regular v or a bold-faced v. Um, so I don't do that. I make sure I put the little arrow on the top, and that's a pretty standard way of doing it. So we'll always write a little arrow on the top when we're talking about a vector. And the arrow just goes left or right regardless of which direction the vector is actually going. The norm or magnitude of that is indicated with these double vertical lines on both sides, sort of like double absolute values. Now, some people will do that with single lines on each side, just exactly like absolute value. It's a little different than absolute value, so I like to go ahead and use the double lines, which is pretty common, but you may see it the other way as well. Okay. So anyway, that's the norm of v is there. So it's the length of this vector here. So for example, this red one, its length is 8. Okay, which was what I've called r here. Okay. So we can give it this vector here in red is in this GeoGebra applet is found by manipulating this slider here or the corresponding boxes here to indicate a radius or magnitude there, the norm, a length, and then this angle beta. Well, it says beta here and it says gamma here. Hopefully I've fixed that. Um, and this gives us this angle right here, the angle it makes with the positive part of the x-axis. Okay, component form, we give horizontal and vertical change from the initial point, the tail, to the tip, the terminal point. And so it's basically a change in x and a change in y with a comma there, but we use these little pointy kind of brackets there for a vector. And so, for example, A is the vector 5, 5, because it goes the right 5. Vector of U goes from A to B is 5, 5. It goes to the right 5 and up 5. Now let me click on this link right here. This is a GeoGebra application activity that I've written. And let me fix something real fast. Okay, I've done a slight upgrade of this and shown this here. So here's a video, here's a screenshot from the slightly newer version of this. So let's go to this version here. So if I click on this link, it'll take me to this here, 2D vector form, and also has our conversions here. So I'm going to go click on this little three dots up here and click open an app. I like that a little bit better, and I can see what's going on here. Okay, so if we look here, we can specify this vector u by specifying the change in x, dx, and the change in y, dy. And we can adjust these by either adjusting the slider here and here, or actually getting in here and typing in a number. Okay, so for example, 4, 2 means we're going to the right 4 and then going up 2. Now, it's actually the same vector no matter where we place it. So if I put it here, if I move it over here, doesn't matter where I put it, as long as it's moving to the right 4 and up 2, it is the same vector. And likewise, this red one is the same vector no matter where it goes. Of course, the red and blue one are different vectors. So that's given, the blue one, the first one there, is given by X and Y components. If I click on standard position, it puts the original point at the origin. But that's not necessary. It could be anywhere we want it to be. The red one, I specify a R, which is the magnitude, this distance from D to E, initial to terminal point, is specified by this R value. That's the norm or magnitude. And then theta is this angle that it makes with the horizontal here. So if you start with 0 angle, it's pointing directly to the right, all the way up to, pi, and then even beyond to 2 pi across here. You could also have the angles going in the negative direction instead if we want. Okay, so you can specify by changing the R and the theta, or you can give it, that's sort of polar form or R theta magnitude and direction form, or we can take a vector like this one and specify by changing the horizontal change, positive or negative, and the vertical change here. Okay, now how can we change between these two forms? Well, it turns out that you got some nice Pythagorean theorem going on here, or some right triangle relationships going on here. So, for example, if this is known to be dx, which is 3, dy is 4, then we could do, of course, then the hypotenuse r then square equals the x squared plus the y squared. So that's the dx squared plus dy squared and square root turns out to be, well, exactly 5 in this case. And then the angle, we know that the cosine of that angle is the dx over the norm, dx over r, or x over r. And so the arc cosine of that would give us an angle between 0 and pi radians, of course. And if we multiply that by the sine, S-I-G-N, or signum of y, then we get the we get the correct angle there. Okay, and the well, that's doing the angle as a between negative pi and pi if we do it that way. We can change from r's and thetas to x and y's because x is just r times cosine of theta and y is r times sine of theta. We'll come back and talk about this a little bit more in just a minute. So there is that again. You can see that. So I encourage you to go to this GeoGebra, pull this up, look at these different things. I actually also have some of these things in a, let's see, let me go to Geogebra. If I go to my calculus, I have a calculus workbook somewhere. Yeah, right here, collected resources. And it has lots of different sections here. If you go to vector functions and look, this has like this one right here is this particular one we're doing. I've also collected some things from other people who do a good job with GeoGebra and looked at some of theirs. So in the next couple of videos, I'll be going over a couple of these things here. For example, this one here is a good one that just talks about how we can animate coming from point A. This says that we got a horizontal component of 9, we want to slide to the right 9, and then down 4 shows you how that component form works for that one. Real pretty little basic, but illustrative one. This one shows you the same sort of thing for magnitude and direction. This one we just move the initial and terminal points around, and that's going to change the length of that vector, which is given there exactly and approximately, and the direction angle given in degrees in this case. And we'll talk about a vector addition a little bit later on. So anyway, this goes around talking about some different parts of that. Okay, moving back to our PowerPoint. Once again, a vector is a directed line segment. It has a magnitude and a direction. When we're talking about vectors, we often talk about scalars, S-C-A-L-A-R. That's a real number which has a magnitude but no direction to it. So distance is a scalar, but displacement is a vector. If I say I'm going 5 miles from wherever I am right now, do you know where I end up? Well, not exactly, because assuming I stay in the same plane, say on the surface of the Earth, I could be anywhere on a circle of radius 5 miles, center where I am. If you allow me to move into 3 dimensions, I could be anywhere on the surface of a sphere 5 miles from where I am. Of course, some of those places will be more likely than others, but we don't know exactly where it is. Whereas if I have a displacement vector, that's something like saying I'm going 5 miles at north 20 degrees east or something like that. That would be a displacement vector. Notice it has a magnitude and a direction. Similarly, speed is a scalar, 14, say, miles per hour, whereas velocity is a vector, 14 miles per hour due south. The initial point of the vector is irrelevant. Two representations of the vector are the exact same vector if and only if they have the same they are the same magnitude and direction. In other words, if the line segments have the same length, they're also parallel and have the arrow on the same corresponding end. So for example, in this picture you see all of these vectors that are drawn in there are the same vector. They're the vector 2, 3. They all go to the right 2 and up 3. It doesn't matter where we start. Now I mentioned this earlier, but converting between component or rectangular and polar forms is we notice that there's a right triangle relationship among the 4 values. Okay, so we have this little right triangle going on here. Here we have x and y, theta is here, and there's r. R we're going to take to be positive. X and y, however, could be positive or negative. Theta then could be any real number for that angle. So it turns out that the cosine of that angle then is, adjacent over hypotenuse, so that's x over r. So x is r times cosine of theta. And the sine of theta is y over r, so that is r sine theta. Now this is no new news to you. If you've done polar coordinates, this is exactly how we convert from r and theta to x and y. If you've done basic trigonometry and looked at the unit circle, points on the unit circle have x coordinates, which are r times the cosine of theta, and y coordinates, which are r times the sine of theta. Okay, so this is really nothing new. We've done this same sort of conversion in many contexts. If we're going the other direction from rectangular to polar, with the vector is the vector xy, R, or the norm of V, is the square root of x squared plus y squared. Well, how do we do that? Well, it's just the Pythagorean theorem, right? The R squared is x squared plus y squared. And solving for R, or the norm of V, that length, it's square root of x squared plus y squared. The cosine of the angle is going to be x over r. Of course, r is the square root of x squared plus y squared. So there are actually infinitely many solutions to that, and all of them are legitimate values of theta. But one way we could do this is to do the arc cosine of x over r, or x over the square root of x squared plus y squared. Okay, that's the arc cosine of the x component over the norm of the vector. And multiply that by the sine, S-I-G-N, or signum, SGN function of y. Remember, the SGN function of y returns 1 if y is positive, -1 if y is negative, and 0 if y is 0. So that gives you some basic ways to convert. Let's look at a couple examples. So, and here they are in the little application again. The red one, we have r is 5, and here it says beta, but it's theta down here, is pi over 3. Okay? And so, in fact, let me fix that. Okay, here's a slightly updated picture here. Okay, so this red vector is this vector going r is 5, theta is pi over 3, and we see that here. And so what is the vector in component form? Well, it's 5, it's r theta, r cosine theta, comma, r sine theta. R is 5, and of course theta is pi over 3. We know cosine of pi over 3 is 1/2, and sine of pi over 3 is square root of 3 over 2. That comes from our basic pi over 6, pi over 3, pi over 2, i.e. 30 degree, 60 degree, 90 degree triangle, which is basically half of an equilateral triangle. And so we can get that basic thing. Of course, 5 halves is 2.5. 5 square root of 3 over 2 is approximately 4.33. And if you look, that's approximately what we have here, determined by the Geogebra app for that one here. Okay, likewise, if we go over here, the blue vector is the vector 2, 3. Go the right 2 and up 3, which I specified here in the application. And we find that the radius there, or norm there of 2, 3, is the square root of 2 squared plus 3 squared. Let's see, 2 squared is 4, 3 squared is 9, 4 plus 9 is 13. So that's the square root of 13, exactly as that length, or approximately about 3.6. And we see that's about what we get here as well, both up here and down here in the graph. Theta is going to be the angle right here. If you look over here in the graph, it should be about 0.98 radians. Over here, we see the exact value is the sine of 3, not sin, but sgn, in other words, positive 1, times the arc cosine of 2 over square root of 13. So the correct answer is arc cosine of 2 over square root of 13. That's the exact value. That's approximately 0.98279 in radians, or 56.31 in degrees. All right, now, so that gives you an idea of what vectors are in 2 dimensions, how they go about looking at their converting between the 2 forms. Now, we could also do vectors in 3 dimensions. Let's pull up this Geogebra app here and take a quick look at that. All right, and so here we can see this red vector here. Now, here's the red vector in just sort of by itself, but unfortunately it's a little hard to visualize what's going on with this red vector when we sort of do it in abstract without any reference other than the axes here. The red axis is the x-axis, the green one is the y-axis, and the blue one is the z-axis. Notice any 2 of these are perpendicular to each other. So we can find points along a plane along the one axis, one number line. We put a perpendicular number line to that, and in such a way, sort of this part here where everything's positive is called the first quadrant. First, second, third, fourth quadrants in the xy plane. We're just looking at it from kind of that way. Okay, it's a regular XY plane. But then now we're going to put a third axis perpendicular to both the other two, another number line going up this way, which is the Z-axis. Okay, and we can find this point. This is in standard position, so the first, or, origin is the initial point. To find the terminal point, which is 3, 7, 6, we go to the right 7 along the x-axis, go parallel to the y-axis 7. So 3 this way, then 7 this way, and then straight up 6. Sometimes this is a little easier to see if you sort of draw a little box around it. And so now if we think about this box, our vector is going from one corner of the box to the opposite corner of this box. This little box is a right rectangular prism. So the components are these, these edges of the box here going around this way. So this is the vector 3, 7, 6. 3, 7, 6, like this. Now, really, it doesn't matter. Remember, it's still the vector 3, 7, 6, no matter where we start it. So it can start, that point can be anywhere. This doesn't change the vector. Standard position is when that initial point is at the origin. Okay, so that shows you something there. We're going to come back to this in a little bit. Let's also look down here on the XY plane. So if we sort of shine a light on this vector and project it down on the XY plane, the shadow would be this little black vector, which has a length I'm going to call R. So this is our X, this is length Y, so this is 3, this is 7. Well, what's R? Well, it's found by a Pythagorean relationship, right? R is the square root of X squared plus Y squared. So that's 3 squared plus 7 squared. And then add that up. So that's 9 plus 49 is 58. So square root of 58, or approximately 7.62, is the length there. Now we also have a right triangle coming up this way, and we can use that to get the length across here. Okay, and then we have the theta down here, which is this angle that this projection makes with the x-axis there. Okay. Okay, so let's go back to the PowerPoint for a minute. So if I call this distance delta x and this distance delta y, and this is r, we have a right triangle going on there. So the Pythagorean theorem says that r squared equals delta x squared plus delta y squared. But we also have a right triangle here that's coming straight out of the plane. This first one down here is laying flat on the floor on the xy plane. But this other one's coming out perpendicular to the xy plane, coming out of the floor, kind of slicing this little box in half, so that we have the base now is r and the height is delta z, and the distance across here we're going to call rho, or the norm of our vector that we're looking for. So in this case, r was the hypotenuse for the one triangle, but now it's one of the legs for the second one. So now we see that r squared plus delta z squared equals rho squared right here. But r squared was delta x squared plus delta y squared. Take the square root of both sides. Everything's positive there. So rho, or the norm of v, is the square root of x squared plus y squared plus z squared, or delta x squared plus delta y squared plus delta z squared, if your vector is delta x, delta y, delta z. So this is a very nice application. Two applications of the Pythagorean theorem produce this sort of three-dimensional distance formula. The distance formula, Euclidean distance, Pythagorean theorem, norm of a vector, those are all essentially the same thing. Okay? So we have this basic setup. Now, it turns out that this actually generalizes nicely to any number of dimensions. Now, it does get harder to visualize once we get beyond 3 dimensions, but vectors can actually have any number of components, and there are actually a lot of real-world applications for even larger vectors, of 14-component vector or whatever, even though we might not want to graph such a thing. And the formula for the norm generalizes nicely. So if our vector is a1, a2, a3 up to an, that's an nth degree, nth dimensional vector. Then the norm is found by just squaring each component, a1 square, a2 square, a3 square, up to an square, and then add those together and then square root. So it generalizes quite nicely. So now we got an idea what vectors are. In the next few videos, we're going to talk about how we can do some arithmetic with vectors. What would it mean to add vectors? What about multiplying vectors? So we'll talk about those over the next course of the next couple of videos.